Hello, hi, welcome to EDUHUNT IIT and NEET Foundation classes. This is Sukumar, your chemistry mentor. We are discussing chapter 1 chemical bonding from 9th class, module 1. See, in the previous class, we are discussing what are the favorable factors for the formation of ionic bond. In that class, I explained that to understand the factors favorable for the formation of ionic bond, first we should understand what are the factors favorable for the formation of cation, and then the factors favorable for the formation of anion. And what is our concept is, if cation formed easily and anion formed easily, then obviously there is an attraction between them. That attraction is called ionic bond. With that attraction, what happens? There is some amount of, let us say 1 mole cations formed and 1 mole anions formed. If 1 mole cations and 1 mole anions comes together because of that attraction to form 1 mole crystal. 1 mole crystal. In that process, what happens? Opposite charges are attracting. Energy is released. That energy is called lattice energy. Why? Because these cations and anions are coming together. They are arranged in a particular pattern. That pattern is called lattice. So it means in the solid ionic crystal, the cation and anion are arranged in a particular pattern, particular sequence. That pattern you can call it as lattice. So simply the total compound, the total arrangement we call it as crystal lattice. So first of all, factors favorable for the favorable for cation formation and factors favorable for anion formation. So let's have a quick revision. Anion formation. So simply low ionization enthalpy, and I discussed how this ionization enthalpy depends on other factors. Low ionization enthalpy. Here for the anion formation, what is important? High electron affinity. I am indicating electron affinity as EA, and next low ionization enthalpy, high electron affinity, and more size is favorable for cation formation, and less size is, and in the case of charge, low charge is favorable. In the case of anion also, low charge is favorable, and in the case of cation, stable configuration favors and here also getting stable configuration is favorable for the formation of anion. Stable configuration favors, and last but not least, so if all these conditions are favorable, if all these conditions are favorable, cation is formed easily. If all these conditions are favorable, that means high ionization enthalpy, comparatively less size, and low charge and stable configuration. Stable configuration, what I mean here? Stable configuration means if an atom is getting stable configuration by gaining electron, then obviously that atom will gain electron. That means anion is easily formed. So if all these conditions are favorable, anion is easily formed. If all these conditions are favorable, cation is easily formed. Since cation anion formed means obviously then there is an attraction between them. That attraction is called ionic bond. But after the formation of cation and anion, what is the next factor which is important is high lattice energy. High lattice Lattice, you can call it as lattice energy or lattice enthalpy. So these are the three factors. What are the three factors? Factors favorable for cation formation, factors favorable for anion formation, and factors favorable or the conditions favorable for the formation of high lattice energy. Then let us discuss what is lattice energy. I will take a separate notes. Lattice energy. Lattice energy. So first of all, to understand lattice energy, first of all, try to understand what is a crystal lattice. For the better understanding or for better explanation, let us imagine this dot as Cl minus. That means we are taking NaCl ionic crystal for the explanation purpose. Let us imagine this dot as Cl minus. And let us imagine this star as Na plus. Okay? Yes. Now I am going to arrange this Cl minus and Na plus in a crystal. In a solid ionic crystal, I am going to arrange this Cl minus and Na plus. Okay? So that we can get an idea how the lattice will be, how the arrangement will be, and what is the pattern like that. See, first of all, what we need to do is take a imaginary cube. Take imaginary cube. Take imaginary cube. This is a cube, but the terminology says that now we are going to call this as unit cell. So I'll explain why this is a unit cell. We'll discuss later, but let us take this. Imagine cubical arrangement. Now there are 8 corners. At the 8 corners, at every corner take Cl minus. That means at every corner you take Cl minus, Cl minus, Cl minus, Cl minus, Cl minus. At every corner there is Cl minus. At every corner there is Cl minus. Okay. And this is the cube. Cube has 8 corners and I have taken 8 Cl minus. Okay. And you know there is a 6 faces, top face, bottom face, right side face. Are you able to understand? Top side face, face, bottom face, right face, left face, front face and back face. Okay. There are 6 faces. If you observe carefully, there is 6 faces. Now at every face center there is Cl minus. At every face center there is Cl minus. How? Top face center, bottom face center, right side face center, left side face center. Up to now it is very easy. Now imagine there is a front face, the face towards me. There is a front face center I am taking here. And what is the back side face? This is the back side face. Back side face center. Okay? Yes. Now in this cube, at what places Cl minus is located? There is 8 corners and at every corner there is Cl minus. There is 8 corners and every corner there is Cl minus. There is 6 phases and at every phase center there is Cl minus. Okay, fine. This is how a cube is formed. Now this cube is called unit cell. Why this is called unit cell? I'll explain later. Up to now you can simply call it as it's a cube. It's a cube now. Now what is important here is in this cube all the important positions are occupied by anion only. See what happens generally in any ionic compound or the cube you taken, important major positions are occupied by anion and the gaps or the voids are occupied by the cation. Why? Because cation is formed by losing electron, anion is formed by gaining electron. Because of that, what happens? The size of anion will be always greater than the size of cation. That's why important major positions are occupied by anion and the gaps are occupied by cation. I'll help you now where the gaps are located. So that's why important positions, that means 8 corners and face centers are occupied by anion only. Now the cation will occupy the gaps. Where the gaps present? See, it's just a description of what actually has. Okay, so to have a better understanding of the crystal lattice, I am going to explain or I am going to give the description for this. Okay, yes, there is an edge center. At every edge center there is Na plus, Na plus. This is an edge, and at the edge center there is Na plus. Every edge center you have to take one Na plus. At every edge center there is Na plus. Okay. I think all the edge centers covered. Along with all the edge centers, there is one Na plus which is inside the cube, at the middle of the cube. I call that place as body center. I'm circling it to show it separately. Okay? Yes. Now this is the basic portion of the entire sodium chloride crystal. You know what is sodium chloride crystal, na? You have seen sodium chloride salt in your house. Sodium chloride crystal, that white colored substance, you call those small particles as crystal. That is sodium chloride crystal. But in that sodium chloride crystal, there is Na plus and Cl minus ions, and that Na plus and Cl minus ions has a proper order of arrangement. There is a sequence, there is a pattern. That pattern or sequence or arrangement is called lattice. Now this is the pattern, this is the sequence, lattice. So crystal, inside the crystal there is an arrangement called lattice. That's why the whole thing is called crystal lattice. But in the entire crystal lattice, this is the basic portion. So this basic portion, this cube is the basic portion. This basic portion is called the unit cell. This unit cell repeats three-dimensionally in all directions to form the total crystal. How I will explain? See, imagine this is the basic unit cell I am calling. For suppose. Okay. So imagine this is the unit cell I am taking separately. Now you call this is the separate unit cell or a cube. Now you can have a cube repeated to the right side like this. You can have one more cube repeated towards the right side like this. You can repeat to the top also, na? Top side like this. Towards the left one. You can repeat to the bottom side, right? Similarly, the bottom of this also, right? Towards the left side also you can repeat, or similarly you can repeat to the outside the board towards me, outside the board towards away from me. So this is the basic portion. This white color cube is the basic portion which repeats three-dimensionally in all directions to form entire crystal. That's why this cube is called unit cell. This is that cube, unit cell. So in every ionic compound there is a particular kind of unit cell. So if you want to study the pattern of the ions arranged in that crystal, simply you can study the pattern or the ratio or the whatever arrangement in the unit cell. The pattern in the unit cell repeats in the entire crystal. How? Let us say. In this one unit cell, how many Na plus? There is 8 corners. There is 8 corners. Imagine carefully. The Na plus present at the corner. The Na plus present at the corner is shared by 8 unit cells. Say corner is common to 8 unit cells. Imagine the room. Imagine your room. Okay, imagine there is 4 rooms in the floor you present, and in the top floor there is 4 rooms. Now imagine the corner of the room. That corner is common to the 8 rooms. 8 rooms, 4 rooms in the floor you present, and in the next floor also 4 rooms. Your room corner is common to the 8 rooms. Like that. This corner is common to the 8 unit cells. So the Cl minus present in the corner is shared by 8 unit cells. So okay, are you getting the point? So from this Cl minus, only 1/8 portion, only 1/8 portion of the Cl minus belongs to this unit cell. Like that, 1/8, 1/8, 1 upon 8, 1 upon 8, 1 upon 8, 1 upon 8. Like that. Here also 1 upon 8. Okay. Similar, like that there is 8 corners. So 8 into 1/8. There is 1 Cl minus coming from the corners. I hope you understand. Similarly, there is 6 Cl minus at the every face center. See, let us take the right side face center. At the right side face center there is Cl minus. That Cl minus is present at the face center. That means a face is shared by two unit cells. The unit cell present to the right and the unit cell present to the left. This unit cell and the right side. So from the Cl minus present at the face center, only half is coming to it, right? So like that there is 6 face center. So 6 into 1/2, there is a 3 Cl minus. What I am saying here is, the Cl minus present from the face center, you are getting only half portion, because a face is common to 2 unit cells. So the particle present at the face center is shared by 2 unit cells. So from this particle present at the face center, only half portion you are getting, like that. Next, there is Na plus. This is then a total how many? 4 Cl minus present in the unit cell. Then what about Na plus? There is Na plus at the body center. So there is 1 Na plus at the body center into complete contribution, because the Na plus present at the body center is not in sharing completely. So 1 into 1 Na plus coming from the body center. 1 Na plus coming from the body center, and there is Na plus at the every edge center. There is Na plus at the every edge center. See, an edge is shared by 4 unit cells. So you imagine this edge. This edge, let's highlight this edge. This edge is shared by 4 unit cells. The unit cell to the right, the unit cell to the left, the unit cell to the, there is 2 unit cells on the board, and from the board, if you move to this side, there is 2 unit cells, right? So this edge is common to the 4 unit cells. So you take this room, imagine the room you present, in the same floor there is 4 rooms. Then what happens? The edge of your room is common to the 4 other rooms present in the same floor. So the particle present in the edge center is shared by 4 unit cells. So like that there is how many edge centers? 12 edges, na? So there is 12 edge centers. From every edge center, only 1/4 of Na plus is coming to this unit cell. So 12 into 1/4, there is 3 Na plus. Okay, a total of 4 Na plus. So if you look carefully, in this one unit cell, there is 4 Na plus, 4 Cl minus. In this one unit cell, there is 4 Na plus, 4 Cl minus. That's why in the unit cell of sodium chloride, the ratio of sodium to that of chlorine, that means cation to that of anion, is 1:1. That's why the formula NaCl. This formula indicates that in the unit cell, the ratio of sodium to that of chlorine is 1:1. Otherwise, there is no such thing like NaCl molecule. See, there is H2O molecule. You can write formula H2O, because that is molecular compound, exist as molecules. But ionic compounds, there is no molecules. So the whatever formula you are writing NaCl is not a formula for the molecule. It is the formula, empirical formula, which is giving the simplest ratio between cation and anion in the unit cell. And I told you already that the ratio present in the unit cell is the total ratio, the same ratio present in the entire crystal, because the entire crystal is formed by the repetition of this unit cell in three-dimensional manner in all directions. Okay. So actually in our textbook or in our material this portion is not given, but I have explained for the better understanding of the lattice. Okay. So the formation of ionic bond or the strength of ionic bond depends upon factors like the how easily cation formed, how easily anion formed, and how strongly lattice formed. Now moving towards the point, what is lattice energy? Now you are well known that what is lattice. This is the lattice. Now what is lattice energy? I will explain here only. Lattice energy. See, in the previous classes I have explained that when 1 mole cation, imagine like this Na plus, there is 1 mole Na plus formed, 1 mole Cl minus formed. Imagine 1 mole cation, 1 mole anion. Then if 1 mole cation and 1 mole anion attracted each other, come close to become 1 mole, to form 1 mole crystal, that means 1 mole crystal lattice. In that process energy released. I have told you previously also, when opposite charges attracts, energy releases. Actually that concept is called the potential energy drop. When opposite charges attract, the plus and minus, when there is plus charge and minus charge particles attracts each other, coming close, then there is a potential energy drop between these particles, that means this system, that is called that we indicate with the potential energy formula also. Okay. Now that energy is called lattice energy. Now what is lattice energy? Let me define. The amount of energy released, the amount of energy released, when 1 mole cation and 1 mole anion in this kind of formula. Okay. Yes, 1 mole cation and 1 mole anion come together to form 1 mole crystal lattice. So the amount of energy released. Okay. Imagine there is 1 mole Na plus, 1 mole Cl minus coming close together to form 1 mole crystal. In this process, in the formation of this crystal, what happens? Energy released. That energy is called lattice energy. Now the point is, more energy released means more stable. More energy released means more stable. If more is the lattice energy, it means in the formation of this crystal lattice, energy lost. More energy lost. More energy lost means more stable, more strong comparatively. Okay. But you can define the lattice energy in another way also. Let me ask you a question. If you want to break this lattice, how much energy I should supply? If you want to break this lattice, how much energy I should supply? Obviously the amount of energy lost when it is formed. See, to break this lattice, you have to supply the same amount of energy which is lost in the process of formation of this lattice. So you can define the lattice energy in both ways. The amount of energy released when the lattice is formed, or the amount of energy required to break the lattice. In both ways, lattice energy will be same. Okay. Yes. Now, like this, if an ionic bond is formed, ionic compounds has some properties like ionic compounds. Properties of ionic compounds. Ionic compounds are generally comparatively stable. comparatively stable. Comparatively means compared to covalent compounds, they are stable. They have high melting points and boiling points. Because strong lattice enthalpy, the melting points and boiling points of ionic compounds are strong. Then good conductors. They are good conductors. Good conductors in molten or in solution form. Molten state or in solution form. They are good conductors in molten state or in solution form. And last, soluble in polar solvents like water. Polar solvents like water. See, these are the general. Okay, these are the general. See, compared to the covalent compounds, ionic compounds are comparatively stable because of the strong bonding. Okay. Because of the strong bonding and strong lattice, you can say the melting points and boiling points of ionic compounds are okay. Okay, they are good conductors in molten state and solution form. See, you take NaCl. NaCl in solid state doesn't conduct electricity. But when you melt NaCl, what happens? The Na plus and Cl minus are now free. They can move freely. That means cation can move towards cathode and anion can move towards anode. That's how they can conduct electricity. So ionic compounds are good conductors of electricity when molten state or in solution form. That means you can dissolve NaCl in water so that Na plus and Cl minus are free now. They can move towards cathode and anode. But solid ionic compound, solid NaCl it's not a conductor because ions are not free. Now, the last but not least, ionic compounds are very much soluble in polar solvents like water. Water is a polar solvent. So, easily dissolve. So, water can easily dissolve ionic compounds. So, whatever factors I have discussed previously, if you apply all the factors, if all the factors are favorable, what happens? Ionic nature increases. If ionic nature of the bond or the ionic nature of the compound increases, then these factors has to increase. That means their stability, melting points, okay. But all the factors are increasing along with the ionic character. But the last factor, that is solubility of ionic compounds in polar solvent. Solubility of ionic compounds in polar solvent is going to be very important because this is not only all the factors, all these factors are depending upon, more or less they are depending upon stability, high melting points and boiling points and good conductance, whatever. All these are more or less depends upon lattice energy only. But this solubility, solubility of ionic compounds in polar solvent is going to depend upon two factors, that is lattice energy and hydration energy. It is going to depend upon two factors, lattice energy along with that hydration energy also. Now we are going to discuss what is lattice energy, what is hydration energy separately. We discussed what is lattice energy. Okay, but now I am going to discuss lattice energy and hydration energy comparatively. Let me discuss. Lattice energy. As I explained, the amount of energy released when one mole cation, 1 mole anion attracted towards each other to form 1 mole lattice. That is lattice energy. So simply, I will indicate the lattice energy with the U letter. Lattice energy is proportional to the charge of cation into charge of anion upon R. R is the distance between the cation and anion. You can take it as a bond length. Okay, R is the distance between the cation and anion. Simply you can take it as a bond length. Fine. Lattice energy. That is how lattice energy depending upon charge and lattice energy depending upon the distance between. Okay, distance between the cation and anion. And simply hydration energy. And simply I will give the formula for hydration energy and let me explain what is hydration energy also. I am indicating hydration energy with the H letter, but that hydration energy is proportional to the hydration of cation separately, hydration of anion separately. That means charge of cation upon radius of cation plus charge of anion upon radius of anion. Okay, this is how. So let me explain what is this hydration, what is hydration energy, how that is going to affect the solubility of ionic compound. Let me discuss. See, for suppose Na plus Cl minus, Na plus Cl minus, next Cl minus Na plus, Cl minus Na plus. Let me take in one more layer of Na plus Cl minus, Na plus Cl minus. Now see, simply in the previous class I explained the lattice, right? This is the lattice, okay, three-dimensionally. Now I have taken just two or three layers. Now between this Na plus and Cl minus there is an attraction, invisible attraction. Ionic bond doesn't any direction. So invisible attraction between them. That attraction is called ionic bond. This is how the entire lattice is formed, right? I have taken only one layer. So this is the crystal. In the formation of this crystal, what happened? 1 mole of Na plus, 1 mole of Cl minus attracted each other. In that process energy dropped. The amount of energy dropped is called lattice enthalpy. So more is the charge, more is the lattice energy, and more is the distance between the ions, less is the lattice energy. That's how the formula is telling to you. Okay, fine. Now what happens if you drop this crystal into water? What happens? Water is a polar solvent. I hope you know the structure of water molecule. It will be like this. Compare it to hydrogen, the electronegativity of oxygen is more. Because of that, what happens? Oxygen will be partial negative and hydrogen will be partial positive. So like that, hydrogen is having partial positive charges. Hydrogen is having partial positive charges and oxygen is having partial negative charge. So there is a dipole, okay, negative pole, positive pole. But anyway, hello. Hello. Yes. So there is a dipole. That is negative pole and positive pole. I am going to indicate water molecule like this, okay? And you have to observe that here there is a partial negative pole, partial positive pole, partial positive pole, partial positive pole. Fine? Okay? Yes. Now look at carefully. This is Na plus. This Na plus is having one full unit, one plus charge, right? Obviously this plus charge is attracted by these partial minus charges. This plus charge is attracted by these partial minus charges, right? And one thing is very clear. This is full 1 unit plus charge. These are partial minus. Because of that, one Na plus can attract so many water molecules. Because every water molecule is having only partial negative. This is full positive. One full positive can attract so many partial negatives. Like that, like this, so many water molecules will surround this Na plus. So many. We don't know how much. So many. Okay. Similarly, let us take this Cl minus. Cl minus is having 1 unit negative charge. That 1 unit negative charge is attracted by these partial positive charges, right? Like that, so many water molecules are surrounding this Cl minus like this, because at this ends there is partial positive charge. Like this. Okay? Like this. So this process of, here what happening actually, this is the sodium chloride crystal. You have taken this crystal inside water. Now water molecules are polar. That polar water molecules are surrounding cation and polar water molecules obviously surrounding anion because of attraction. this process or the phenomena in which cation and anion are surrounded by solvent molecules is called solvation. This process is called solvation. This process is called solvation. And if you know that solvent is water, you can call that solvation process as hydration. Solvation or hydration. Whatever. But the point is, in this solvation process also, what is happening? The opposite charges are attracting, because cation is positively charged and that is attracting the partial negative charges on water molecule. I have told you previously, when opposite charges attracts, energy releases. Right? Yes. So, in the solvation of cation and solvation of anion, that means in the process of hydration, solvation or hydration, okay, in the process of this hydration also energy released. That energy is called hydration energy. Now, if the hydration energy is more than lattice energy of this crystal, then what happens? The lattice breaks inside the water. When the lattice breaks inside the water medium, the cations and anions are free now. That process is called dissolution, and you will call this process as, or you call this process as that salt dissolved in water. So, when this salt has to be dissolved in water, what is important? Hydration enthalpy or hydration energy must be greater than, or hydration energy must be greater than or equal to lattice energy. See, if hydration energy equal to lattice energy, then also lattice breaks. Or if hydration energy more than lattice energy, then also lattice can be breaked. So simply I told you previously, what is lattice energy? When some 1 mole cations or 1 mole anions forms 1 mole crystal, the energy lost is called lattice energy. Now if you want to break this lattice, what amount of energy you have to give? Lattice energy. So now when in the form of hydration, we are supplying that lattice energy. Now in the form of hydration, we are supplying that lattice energy. Okay. So the point is, I am going to erase this. I explained this phenomena, but the point what you need to remember is, if hydration enthalpy is greater than or equal to lattice enthalpy, then salt is soluble. Similarly, if hydration enthalpy less than lattice enthalpy or lattice enthalpy greater than hydration enthalpy, obviously you call then salt is insoluble. What it means? You have taken the crystal inside the water, solvation takes place, but in the solvation the energy released is not that much as the lattice enthalpy. That hydration enthalpy not capable of breaking the lattice. So lattice remains strong inside the water medium also. So if the lattice is not breaking, it means the salt is not dissolved. So this is the condition required for the dissolution of salt, for the solubility of salt inside the. So hydration enthalpy must be greater than lattice enthalpy. Note it, I will explain the further concept here only. Okay. Now, how to determine whether the lattice enthalpy, see, in any sequence of salts, you may be, in the question paper you may be given with some examples, and you may be asked to find out the increasing order of solubilities or decreasing order of solubilities. I will give you simple explanation and trick for you to understand or to describe how, in which way the solubility is increasing. I hope you note this. I will erase this. See, what is important here is, if the difference in the size, this is important, the difference in the size of cation and anion increases, okay, if the difference, I hope you understand my notes, okay? If difference in the size of cation and anion increases, then the decrease in lattice energy is more than decrease in hydration energy. This is quite important. This one thing you need to remember. You have given with some examples. For suppose, imagine from left to right, you have given it 4 examples. In those examples, the difference in the size is increasing. Now, if the difference in the size increases between cation and anion, what happens? Lattice energy, so both decreases. Actually, lattice energy decreases, hydration energy also decreases, but the decrease in the lattice energy is more compared to decrease in the hydration energy. Because of that, what happens? At any point of time, hydration will be more than the lattice. So if the hydration energy is more than lattice, then solubility increases. This is one thing you need to understand. Okay, let me apply this concept. For suppose, let us take an example of lithium fluoride, lithium chloride, lithium bromide, lithium iodide. Okay, first of all, you must understand what is the ion which is kept constant in all these examples. In all these examples, cation is constant, lithium cation, and lithium cation you have to identify the cation as the small cation. See, generally Li plus cation, Na plus cation, these two from the first group, 1A group, and Be2 plus cation from 2A group. Consider these cations as the small cations. Okay. Similarly, for the case of anions, F minus. Okay, F minus is the small anion, H minus is the small anion, OH minus is the small anion. These ions are small anions, and rest of the ions, these are small. And rest of the ions, normal ions like a group of atoms like CO3 2 negative, SO4 2 negative. So these are large anions. Okay. So these examples are enough. Okay. Yes. Now among these, identify the cation, because here cation is constant and anion is changing, right? Yes. Cation is lithium. Okay. So all are small cations. You know, in a group top to bottom, size increases. The first member lithium and the second member we have considered as small, and in the next group beryllium only considered as small. Okay, remember this. Yes. Now cation is small. Now as you move in this direction, what happens? F minus. In this direction, size of anion is increasing, because fluorine, chlorine, bromine, iodine, in a group top to bottom size increases. So in this direction, difference in the size is increasing. If the difference in the size increases, what happens? Lattice energy drops, hydration energy also drops, but the decrease in the, see, this is, let us say, this is hydration energy, this is lattice energy. If the difference in the size increases, both will decrease. Lattice energy decreases, hydration energy decreases, lattice energy decreases. But the decrease in the lattice energy is more compared to hydration energy. I'll explain again. Let us consider this level, this my right hand as hydration energy level, this much of hydration energy, okay? This much of lattice energy, imagine. Now if the difference in the size increases, what happens? Both decreases. Hydration energy decreases, lattice energy also decreases. But comparatively, the decrease in the lattice energy is more than the hydration energy. So at any point of time, what happens? Hydration energy will be more than lattice energy. So in this direction, as you move, what happens? Hydration energy more than lattice energy. So solubility increases in this direction. Solubility increases. And you may get wrong answer if you try to explain the solubility of these members according to the polarizing power or polarizability. If you try to explain the solubility of these compounds depending upon polarizing power or polarizability, you will get wrong answer. Let's try that one also. In this direction, solubility increases. That means lithium chloride is iodide more soluble than bromide. See, in this direction what happens? Cation is kept constant. That means polarizing power constant. Anion size increases. Anion size increases, what happens? Polarizability increases. If polarizability increases, what happens? Covalent character increases. Covalent character. So that polarizing power and polarizability I'll explain in the next class. But the point is, see, if the anion size increases, what happens? Polarizability increases. If polarizability increases, covalent character increases. It means compared to lithium fluoride, this is more covalent, more covalent, more covalent. See, more covalent means less soluble in ionic. So according to that point, this should have least solubility, but that's not the factor. This is the deciding factor. Always. Simple logic, simple logic. You check the direction in which the size is different. Okay, if the difference in the size is increasing, what happens? Difference in the size increases, what happens? Lattice energy decreases, hydration energy decreases. But the decrease in the lattice energy always more decrease than the hydration. So hydration will be more than the lattice as you move like this. Okay. For better understanding, try to explain this also. BeF2, BeCl2, BeBr2, BeI2. Now here also, what is the increasing order of solubility or decreasing order of solubility? Now the point is, you have to identify the cation. The common thing is cation here. Which cation? Beryllium. Beryllium is the first member of which family? Second group, small cation. So small cation, small anion. So F minus. In this direction, what happens? Size of anion. That means anion also increasing. Size of anion increasing in this direction. That means in this direction difference is less because beryllium is a small cation. Okay, small cation, small anions means difference is less. That means in this direction size difference is less. In this direction size difference is more. I'll again explain. First consider beryllium as the small cation. If small cation is coupled by small anion, size difference will be less. If small cation paired by large anion, difference in size will be more. Okay. So beryllium is a small cation. Now in this direction, small cation paired by large anion as you move. That means in this direction, difference in the size increases. If difference in the size increases, what happens? Lattice energy decreases, hydration energy decreases, but comparatively the decrease in the lattice energy more than hydration energy. So hydration energy greater than lattice energy. So in this direction, solubility increases. Solubility increases. So the point, sir, why sir? Why sir, as the difference increases, why the, I have told in the case of hydration enthalpy, what I told, if the difference in the size increases, what happens to the hydration enthalpy? Why it is less? See, hydration enthalpy is depending like cation size upon size of cation charge on cation upon radius of cation plus charge on anion upon radius of anion, like this, right? See, if the difference in the size of cation anion is large, for suppose, what happens? Let us say this is the cation size and this is the anion size. Now compare it from here to here, what happens? The charge density is more because the same 1 unit positive charge, 1 unit negative charge. But the same 1 unit positive charge is present in small cation. So what happens here? The charge density is more. So more water molecules are surrounded here compared to that one. Compared to this one. Here less number of water molecules. But here more water molecules, a huge number of water molecules. It means, for the better understanding, let me explain this. For suppose if hydration energy is 100, for suppose the total hydration energy is 100, among this 100, 92 will be contributed by cation and the 8 will be contributed by anion. So what happens if the size increases? If the size of anion increases, you increase the anion size. That means this denominator is increasing. If this denominator increases, overall this fraction value decreases. That means this 8 will decreases. If 8 will be decreased to, it will become 7 or 6, or what happens to the total? Total will be near 100, na? Because this total, in this total energy, the major contribution is from cation. So hydration enthalpy is largely depends upon cation. That is the smallest one. So if the difference increases, if the difference between size, if the difference between size of the cation and anion increases, the hydration enthalpy is that means the value of the hydration enthalpy is not changing that much as the value of lattice enthalpy changing. Okay? Yes. So this is how the ionic compounds or the solubility of ionic compound is depending upon the lattice enthalpy or hydration enthalpy. In the next class, we are going to discuss what is polarizing power or polarizability and how it is going to decide the covalent nature in an ionic compound. Thank you.